So we have to proceed with our axiomatic approach to quantum field theories, to conformal field theories. And the next absolutely indispensable tool is going to be the operator product expansion. So just to remind you what the OPE is in the general conformal field theory, so we take two operators which are close to each other, have to be closer than any other operator in the correlation function, and we replace them by a sum of other local operators inserted at 0, and the power of x in this formula is going to be fixed just by scaling arguments of the dimensional operators on the left-hand side and the right-hand side. That's clear. There's going to be an overall constant here, which is a free parameter. That's also clear. But so that's going to be the leading OPE. And when you do conformal field theory in 2 dimensions, you often just stop here. But of course, you keep in mind that there are also all the subleading terms in the OPE. And for us, they're going to be absolutely crucial. So these subleading terms, the important thing about them that their coefficients, so the structure of these terms is more or less like this. There's going to be the term proportional to the first derivative of OK, then there's going to be a second derivative, and here you see that there are different ways to contract the indices, and you always have to contract the indices with x, because that's the only vector available to you. And there are these coefficients which come up in higher orders, and the important thing is that these coefficients are completely fixed by conformal symmetry. So they're just functions of the dimensions of the operators and the dimension of space-time. And there are various ways to fix these coefficients, but the simplest way, perhaps pedestrian simplest way, is just to notice that if you take this OPE and if you plug it into the 3-point function, so let's take the 3-point function y, oj, ok, and let's replace oy, oj by the OPE, then since we know what the 3-point function is at all positions, we can require order by order that the expansion of this expression that you get from here should agree with another expansion that you will get from the OPE, and which depends on these coefficients alpha, beta, and so on. And if you do it, you will be able to recover all these coefficients. And just to give you an example of the first few, suppose that you take the dimensions of these operators equal, and the dimension of the third operator delta, then you find that this alpha coefficient is delta plus 2 over 8 delta plus 1, and beta is this. And so you see in particular that beta depends on the dimensions of space-time, while alpha does not. This is not accidental, as a matter of fact. So because beta, you see that beta is proportional to x squared, so it's going to be, so we are doing CFT here in Euclidean signature, but you could also consider analytically continue all the correlators into the Lorentzian metric, and then one interesting limit to consider is the light cone limit. So when x becomes light-like. We are not going to do it in these lectures, but if you were to do it, then you would find that near the light cone, this operator in the OPE survives, while this operator just drops out. It's subleading because it's multiplied by x squared. So it is a general fact which was known since the 70s, that these coefficients which are subleading on the light cone, they depend on the space-time dimension, while the ones which are leading on the light cone, they're actually completely universal. They depend just on the dimension of the operator. Another thing that you see from these formulas is that these coefficients, in this particular case, they depend only on the dimension of the operator OK, but not on the dimension of operators OI and OJ. This is because we fixed them equal. So if we were to take them different, then these coefficients would also depend on the difference of the dimension delta I minus delta j, but not on them independently. But you can work it out. So this has actually been already worked out in the 70s by Sergio Ferrara and by other people, these expansions. So this is something that you just sit down and do, and you can do it to any order. Now, if you now will go back to the Ising model, then what do we know about the OPE structure of the Ising model? Well, since we have a Z2 global symmetry, we know that the OPE of two Z2 odd operators is going to be Z2 even, and odd times even are going to be odd, and so on. And for example, if you look at the OPE of two spin fields, sigma times sigma, then you will discover in this OPE all the other operators that we discussed, all our friends, epsilon, subleading epsilon, the stress tensor, C, but also you will also discover the unit operator. The unit operator is also always present in the OPE of an operator with itself, and it's needed to reproduce the two-point function of the operator, because if you take the two-point function here on the left-hand side, and on the right-hand side, we will have here the unit operator one-point function, which is 1. And here we will have the one-point functions of all these other operators. But the one-point function of an operator in the conformal field theory is 0, unless conformal symmetry is broken spontaneously, but which we are assuming it's not. So you really need this operator, unit operator here, with the coefficient of this operator, which is fixed by the normalization of the spin field. Since we usually normalize the two-point function of any operator to 1 divided by a power, it means that the coefficient of the unit operator is going to be equal to 1, while the coefficients of all the other operators are free parameters, which need to be determined to solve the theory. And so I told you that we know a lot about dimensions of these operators in the Ising model. But we know essentially nothing about the OPE coefficients. So the older renormalization group studies, they did not provide any results about the OPE coefficients of these operators. So they have to be determined. And analogously, if we take the OPE of sigma times epsilon, then you get here some Z2 odd operators, like sigma, subleading sigma, and which is going to be irrelevant, and then operators, other operators which we didn't even discuss, so nothing is known about them. And an interesting thing about this OPE is that the first OPE, as you see already from here, it will contain only operators of even spin, while this OPE will contain operators of all spin. So let us explain why this is so. This is a general fact of a conformal field theory. If you take an OPE of two identical scalars, then it only contains operators of even primaries of even spin. So here's the proof. So if you take the three-point function of a scalar, scalar, and spin L operator, then it's up to us to use conformal symmetry to put three-point functions at any positions in the space that we like, because the conformal group, the finite dimensional conformal group, is sufficiently rich to assign 3 points in the space to any given positions. Now, once you do it, the fourth point is going to be free, but 3 points you can put anywhere. So let us put it at points x, minus x, and 0, where x is any vector. Now, if we were to do it like this, then this 3-point function, it can only depend on x, because there is nothing else here. And since it has to be a tensor in these indices, mu1, mu2, mu-l, the indices of this operator, it can only be x mu1, x mu2, and so on, x mu-l. There is nothing else here. Moreover, if we are assuming that these two scalars are identical, so this 3-point function should be actually invariant by mapping x to minus x. And so this means that this 3-point function vanishes if the spin of this operator O is odd. So it vanishes at this particular configuration of points, and by conformal invariance, it means that it vanishes at all positions. And so it means that this OPE coefficient is simply 0. The odd spin operator doesn't appear. So end of proof. And you see that in order to make this argument, it was absolutely crucial to have conformal invariance. And for example, you see that the argument is only about primaries. It's of course not true to say that no odd spin operator appears, because if you take a primary which is even spin, you apply to a derivative and you get the descendant which is odd spin, and that descendant will also appear in the OPE. So there is no statement to that kind. And notice another thing, that I always speak here about operators. So I just say spin L. What does it mean? It means that I'm considering operators which are symmetric traceless tensors with L indices. But of course, representation theory allows primary operators in conformal field theories with other representation properties under the Lorentz group. For example, you can have an antisymmetric, a priori you can have an antisymmetric primary, antisymmetric tensor primary. Of course, in 3 dimensions, you can always transform antisymmetric into symmetric by contracting with the epsilon tensor. But in 4 dimensions, for example, this is not possible. So you really have these guys as extra fields. But notice that these guys, if they exist, they can never occur in the OPE of 2 scalar fields. So again, by the same argument, if you take 2 scalars and now they don't have to be identical, so and here you take some guy which is an antisymmetric tensor, but you still have only one vector in your disposal, x, and you cannot construct an antisymmetric tensor out of one vector. So that operator just cannot occur. So that's it. Okay. Now, this was supposed to be the start of the second half, so I'm going to recap a little bit. So what we, just to stress that we said that there is, to solve a conformal theory, it means to find this set of numbers, which we call CFT data, which is just the spectrum of local operators, and these OPE coefficients Fij, which enter also in the OPE, and the rest of the OPE is fixed by conformal symmetry. So if you know these numbers, then you can determine 2-point functions. Of course, they're fixed by scaling dimension. 3-point functions, because they're just proportional to f's. But you can also determine higher-point functions by using the OPE. So for example, here I'm showing that if you want to determine 5-point function, then you can take these 2 operators, you can collide them by the OPE, and you can replace this 5-point function by a sum of OPE coefficients acting on the 4-point functions. So if you do it repeatedly, you will reduce your correlation function to correlation functions that you do know, to 3-point functions or even to 2-point functions. So at least in principle, if you know the CFT data, you know the theory. So perhaps one comment should be in order that there are some conformal field theories which contain other observables. For example, if you take n=4 super Young-Mills, then it contains also the Wilson loop observables. And you can invent other observables by putting defects, other types of defects into conformal field theories. And so eventually you should also learn how to describe those observables in this axiomatic language. which I'm not going to do in this course. So here I'm really focusing on the correlation functions, which are the simplest possible observables that you can imagine. So back to the OPE. So one trivial fact that if you take the 3-point function, I thought I changed the batteries, but it didn't really do anything. So if you take the 3-point function and you try to compute it by the OPE, so you try to reduce it to the 2-point functions by using the OPE, so, and you can do it in 3 possible ways. You can either collide OI or J or other pairs. And you can check, and okay, this is a simple check of consistency of the whole construction, that independently of which pair you use, it always is going to give you the same expression for the 3-point function on the right-hand side. So this is consistent. But it's not going to be automatically consistent for 4-point functions. And this is really the heart of the matter. So let us review how it goes. So if you take a 4-point function, then we can do things in 2 ways. We can either collide the O1 with O2 by the OPE and O3 by O4. And if you do this, you get in the right-hand side this sum. So you get a sum of 2-point functions acted upon by the OPE coefficient function C. One depends on the difference between operators O1 and O2. Another which depends on the difference between operators O3 and O4, multiplied by these OPE coefficients. And so these OPE coefficients, okay, they characterize the theory, but this object here, it's completely fixed by conformal symmetry, again. So just like, because the OPE is fixed, this is fixed, so this object is fixed. Fixed in terms of what? Fixed in terms of the dimensions of the operators, the dimensions of the exchanged operator, and the space-time dimension. So this object is called conformal partial wave. And so we see that the 4-point function can be replaced by sum of the OPE coefficients, products of OPE coefficients, times conformal partial wave. But there are partial waves in the S channel, and there are also partial waves in the T channel. You can, instead of doing this, you can collide O1 with O4, O2 with O3, and you get a sum which is a different sum, because it involves generally different OPE coefficients, because here you have operators which couple to 1, 2, and here you have operators which couple to 1, 4. And the dimensions of these operators can be different. And even if the dimensions and the OPE coefficients are the same, the kinematics is different. So in S channel and T channel, kinematics is different. So it's not at all trivial that these 2 things should agree. It's not automatic. So let us do it a bit more explicitly for the case of 4 identical scalars. So if you take some scalar phi and we consider its 4-point function with itself, then it's known that in this case, conformal word identities are not sufficient to fix for you the functional form of this correlator, but they tell you that this correlator is equal to some arbitrary function of the cross ratios, GUV, divided by some powers of the distances which are just there to ensure conformal invariance. And the cross ratios, these are, so there are 2 cross ratios, 2 independent cross ratios. They're independently, they're conformally invariant by themselves. And so this whole object is conformally invariant for whatever function G is. So you don't know in general what this function G is. It's an important observable, but as I said, if you know the CFT data, you should be able to compute this function GUV and using the OPE. And that's how it goes. So you take this 4-point function, you collide, for example, you choose the S channel, so you collide phi1 with phi2. phi 3 with phi 4, and you get this conformal partial waves. But these conformal partial waves, you can show quite generally that the conformal partial waves have exactly the same transformation properties under the conformal group as the 4-point function itself. This is actually not at all a complicated fact, because it follows from the fact that the conformal partial wave is defined by putting together conformal OPEs. So conformal OPE is conformally invariant. So you can, so if you take the conformal partial wave and act on it with a generator of conformal groups, so if you want to derive the conformal word identity, then those generators that act on the operators phi, you can push and replace them by the generator which acts on the operator O by the invariance of the OPE. And since the 2-point function of the operators O is also conformally invariant, so you prove that exactly the same word identity which was satisfied by the 4-point function is going to be also satisfied by the conformal partial wave. So this shows that, that the conformal partial wave again is going to have the form of some function of u and v divided by the same power of x's here as the 4-point function. Except that this function of u and v is fixed by conformal symmetry. So it's called conformal block. So it's a very fundamental object, and which you can compute once and for all. You can tabulate these functions. If you know it, then you obtain that this function g of uv is equal to 1. And 1 here, it's the contribution of the unit operator to the OPE. So these conformal blocks in general are complicated functions. I'm going to talk more about them later on. But the conformal block of the unit operator is a very trivial function, it's just equal to 1. So it makes sense to separate it. And here you will have conformal blocks of all other operators with their OPE coefficients squared. So this is a formula which solves the problem of determining the 4-point function out of CFT data. But here I'm just applying it in the S channel. But now suppose that I were to apply it also in the T channel and require that the two things agree. So in this case, in the case of 4 identical scalars, this is very easy. It's very easy to write down what is the equation that you get. Because in this case, S channel and T channel are related by crossing symmetry. So to go to the S channel to the T channel, you just replace point x1 with the point x3. And you do nothing else. So it's the same operators. And so it means that the 4-point function actually has 2 expansions. It looks like GUV divided by x12, x34, or it can also be written as G of VU divided by x14, x23. Because this transformation, x1 and x3, it interchanges U and V. But it's the same 4-point function, so the two things should agree. And this means that this function GUV satisfies this functional relation. So GVU is equal V over U to the power delta phi times GUV. So this relation is a consistency condition on the CFT data. So the function GUV can be computed by using this formula, but then we have to impose that this formula, the function GV given by this formula, satisfies this functional equation. And this is going to be not automatic, in the sense that it's not satisfied term by term. You can already see it. Let's just take the first term here, 1, and just ignore the rest. Well, clearly, the function which is equal to 1 is not going to satisfy this relation, because here you get 1, and here you get V over U to the power delta phi. So only if all the other operators are also present and they conspire, and then you can hope in the infinite sum limit to recover this relation. So Another interesting comment to make about this equation is that you see the original 4-point function, it involved x's. It involves the function of u and v and involved x's. But this relation itself, we completely got rid of the x's. We reduced it just to a functional relation on the function of u and v. This has an interesting philosophical consequence that suppose that you want to define what it means to have a conformal field theory in 4 minus epsilon dimensions. Because we discussed here the epsilon expansion and so on. And so the epsilon expansion assumes that there is such a thing as a conformal field theory in 4 minus epsilon dimensions. Now, is this theory in 4 minus epsilon dimensions just an intermediate trick? So you do the computations using Feynman diagrams, but in the end of the day, you always have to put epsilon equal to 1? Or is it really, or does it really exist as a mathematical object? Well, and if yes, then what is the definition of it? And then the answer is yes, it exists. It exists non-perturbatively. And this equation provides a non-perturbative definition of this conformal field theory. Okay, this equation and its analogs, because I only considered one 4-point function, but of course you have to do it for all 4-point functions. Because here we have an equation which involves just two variables, v and u. And in any number of dimensions, you have the same number of variables. And as we will see, the conformal blocks, they depend on the number of space-time dimensions just as an analytic parameter. So nothing stops you from taking this equation and study it in 4, 3, or 3.5, or whatever number of dimensions. It's as mathematically well-defined in 3.99 as in 3 dimensions. So that's it. We arrive at the definition, at the axiomatic definition of conformal field theory. So we analyzed here the case of 4 identical scalars, but now we can do the same thing for 4 non-identical fields, and we're supposed to do it for scalars and also for all fields of higher spin. And we have to impose that the conformal partial wave decomposition in the S channel is the same as in the T channel for all u and v. So as I said, the agreement is not automatic, so it provides for you a constraint on the CFT data. Which has actually been discussed already in the 70s, this constraint. And what people believed back then is that this constraint should essentially amount to the definition of what a conformal field theory is. So in order to define a conformal field theory, you don't need a Lagrangian. You just need a set of numbers. Then you check this constraint. Is it satisfied? Okay, then you have a theory. If it's not satisfied, then you just throw it away. So this is the definition. Well, it's not full definition for 2 reasons. Because we know that in 2 dimensions, it's not a full definition. Because in 2 dimensions, you can have a theory which satisfies this constraint. But it's not a full theory. It's a truncation. It's a truncation of some theory to a subset of operators. Because imagine, let's just take the 3-dimensional Ising model. It has a Z2 symmetry. Let's truncate this theory to the set of operators which are even under Z2 symmetry. Then this truncation is still going to satisfy this constraint. Because from Z2 even to Z2 even, you will always get Z2 even, so you will get a coupled system of equations which is going to be satisfied. But it's not the full theory. So in the same sense, in the 2 dimensions, also these truncations give you not the full theory, but in 2 dimensions, we know how to check that your theory is not complete. And the check is provided by modular invariance. You compute the partition function of the torus, which we will also encounter later on, and you see if it's modular invariant or not. If it's not modular invariant, then it means that you are missing some states. Then you think how to complete your theory and so on. So perhaps also in 3D, so in 3 dimensions, this constraint of modular invariance is much more complicated. But morally, you think that it should also exist. You should not be allowed to truncate the theory arbitrarily to some subsector. But in any case, this system of equations, which is known as conformal bootstrap system, it should provide you a good, just like in 2 dimensions, it should provide you a good 0th order approximation to what CFT is. So the hope is that just like in mathematics, you can take linear algebras, you can write down the Jacobi identities which encode for you the fact that it follows from the commutator, and then you can just analyze these Jacobi identities and you can derive the Cartan classification of all the algebras. So in the same sense, you should be able to just analyze this system, and it should spit out for you all possible conformal field theories which exist in this world. So some discrete families, or maybe there are going to be some continuous families which are associated with marginal perturbations. Somewhere, the n equal 4 super Young-Mills is going to be somewhere there. So this is a very ambitious goal, right? And we're still very, very far away from just writing a code, pressing the button, and it spits out for the list of CFTs. But I think it's a noble goal to try to work to. So I will tell you what is known.
When you do, like, for example, 4 minus epsilon,
Yeah.
can we imagine doing this like 6 minus epsilon, starting from 6 dimensions?
Yeah, you can. You can actually. If you take phi cube theory, so phi cube theory, of course, with the real coupling, it's not a well-defined theory. It doesn't have the right Hamiltonian. But if you take an imaginary coupling for phi cube theory, and if you consider it in 6 minus epsilon dimensions, it has a critical point, which is a conformal field theory. It's a non-unitary conformal field theory. And that critical point extends all the way from 6 dimensions to 5, 4, 3, 2 dimensions. And it actually, in 2 dimensions, it gives you the simplest non-unitary minimal model, the Lie-Yang singularity theory. So you can do also such things starting from 6 dimensions. Well, it is assumed that you should, you mean there is a third possibility? Yeah, it is assumed that you should also do it, you should consider also U-channel. Yeah.
Is it automatic that the U-channel is decided if SMT agree or not?
No, it's not automatic. No. So, what is automatic is that if you solve the system for 4-point functions, then it's of all operators, then it's also going to be satisfied for high-point functions. That you can convince yourself that if you start with a 5-point function, you apply this OPE associativity twice, and then you see that if for 4-point functions it works, for all 4-point functions, then it's only going to work for 5-point functions and so on. So really, you can limit yourself to 4-point functions. So this idea, this conformal bootstrap idea, it was, of course, realized in 2 dimensions, but using some extra tricks, unfortunately. So the way it works in 2 dimensions is that we have the luxury of having all these extra raising and lowering operators, which allow us to form much bigger multiplets, Virasoro multiplets. And in particular, now it can happen that your theory has a finite number of Virasoro primary fields. Something which can never happen for quasi-primaries and can never happen for primaries in higher dimensions. And one famous, so in particular, it happens for unitary conformal field theories of center of charge less than 1. So if the center of charge is less than 1 of this form, so the theory is unitary, then you not only do you know that you have infinitely many primary operators, but you also know dimensions of all of them. So it's just this list, the Katz table. So if you vary the integers s and r in this range, then you just get all possible dimensions of fields in your theory. But you don't know the OPE coefficients, so the representation theory doesn't tell you that. So this, by the way, so these dimensions, they follow from, you can recover them in several ways. So these are the so-called degenerate fields. So they are annihilated by some extra raising operator. But you can also recover these dimensions by imposing unitarity. So if the dimensions are different from these values, and if the center of charge is less than 1, then by acting on them with some raising operator, they will sooner or later recover a state of negative norm. So this just shows that unitarity in 2 dimensions is much, much more powerful. Unitarity bounds in 2 dimensions are much, much more powerful for C less than 1 case than in higher dimensions, where we reviewed what the unitarity bounds were. So if you know the dimensions, and if you know that you have finitely many fields, then the problem of determining OPE coefficients is the problem of bootstrap, except that it's a very simple bootstrap. It's linear algebra. You just have to solve a system of linear algebra, of linear equations for finitely many numbers. And this has been done. In the simplest case, it was already done by BPZ in their paper. And that's it. That's the end of bootstrap. Yeah.
Is this statement also correct in higher dimensions, that given the spectrum of operators, the OPE coefficients have only one solution?
No, I didn't make that statement. But it might be true, but yeah, we currently don't really have a way to prove that. So the difficulties in 3 dimensions, there are 2 difficulties. So first of all, the number of primaries is always infinite, since you're not doing linear algebra. You're doing linear algebra in an infinite dimensional space, where, of course, it's much less clear how to do it. And the second thing is that the dimensions of the primaries are also unknown. So they scan ranges, and they also have to be computed. And so and the OPE coefficients enter here in a relatively simple way, but the dimensions of the primaries, they enter into the conformal blocks in a very, very complicated way, in a very complicated and nonlinear, non-polynomial way. So you lose simplicity, you lose a lot of simplicity. And one philosophical problem that you have to face, even before you start looking at this system, is whether this system is mathematically well defined. Is it a convergent equation? So there are infinitely many terms here, right? So because if it's not convergent, then might we not run into the same difficulties that people doing epsilon expansion are running into? So this is the reason to get really worried. So the number of primaries, not only is it infinite in conformal field theories, but it actually grows exponentially fast as you go up with dimension. And here's how you prove it. You look. So this allows us to introduce this idea of radial quantization, which is well known in 2 dimensions, but also works in higher dimensions. So if you take conformal field theory in flat space and you quantize it radially around the origin, then you can take this picture and you can do a Weil transformation from the metric of flat space to a metric of the sphere, d-1 dimensional sphere times time. And this Weil transformation really makes the metric uniform in time, this Euclidean time. And so all correlation functions from the flat space can be transformed onto this cylinder. And the nice thing about this picture is that on the cylinder, you really are doing just quantum mechanics. So the cylinder geometry has time translation invariance. So the quantum field theory in this geometry means that you have a Hamiltonian on the sphere. And everything is described by this Hamiltonian, by the Hamiltonian evolution. And another nice thing is that the spectrum of this Hamiltonian is known. Because via the radial quantization, the spectrum of this Hamiltonian is in one-to-one correspondence with the spectrum of local operators in flat space. So the energies on the sphere are just equal to the energies of operators, to the scaling dimensions of operators in flat space divided by the radius of the sphere, which is the only scale in this problem. And okay, in even dimensions, there is also Casimir energy in this equation, which is constant divided by r, but okay, I didn't write it down here, but it's not going to play a role in our discussion. In odd dimensions, in 3 dimensions, there is no Casimir energy, because there is no Weil anomaly. So now, once you know that, you consider the partition function in this geometry. So it means what it means is that you compactify the time on the thermal circle, and so you consider the partition function, so the sum of minus energy over time for all states in this geometry. And so you get a certain sum over the dimensions of your theory. And now you consider the high temperature limit. So the high temperature limit means that the temperature has, so the length of the circle, the inverse temperature, has to be much smaller than the size of the sphere. So in this high temperature limit, you expect that the curvature, that the fact that your theory lives on a sphere of finite radius, should be essentially irrelevant. So the sphere acts as the infrared regulator, but the curvature of the sphere shouldn't matter much. So you expect that in this limit, the free energy which is the log of the partition function, should go like the volume of the sphere times some free energy density, which is the same free energy density as in flat space. So as such, this free energy density depends only on the temperature, and by dimensional analysis, it should depend on the temperature as temperature to the power d-1. So by the way, these steps that I'm going through, they should be familiar to you from the 2-dimensional conformal field theory, because that's how you derive Cardy's formula for the density of states in the 2-dimensional conformal field theory. All these steps go through. Except that for the Cardy formula, this cylinder is, so there's one step which is simpler, because the cylinder in that case is actually the circle. So the curvature of the circle is 0. So you don't even have to make an argument that in the high temperature limit, the curvature of the sphere is small. In that case, the curvature is just 0. But you do have to make an argument that the boundary conditions somehow don't matter. So that's it. This is the partition function, and you know that in the high temperature limit, it behaves like that, with the density of free energy growing like T to the d minus 1. So clearly, in the high temperature limit, you are becoming sensitive to the density of states and higher. In the high temperature limit, you are becoming to the density of states and higher dimensions. And you will believe me that by doing a stationary phase, you can derive that the number of all states, so because here we are in the partition function, we have to include all states, independently of whether they are primaries or descendants, their number should grow. You find that in order to reproduce this behavior, the number should grow exponentially, should become exponentially large. And this behavior is e to the exponential times to the power 1 minus 1 over d. So for d equal to 2, you recover the square root behavior as in the Cardy formula, but for high d, it's a different power. And so this argument tells you the density of all states, but the density of primaries is going to be given asymptotically by the same expression, simply because that we know how many descendants a primary can produce at a high level. And in high-dimensional theory, since there are so few, since there is only one raising operator, the momentum generator, or rather d of them, d components, this number of descendants is very small. It grows only as a power of level. So it cannot beat this exponential in no way. So it cannot give you this exponential. To get the exponential, you really have to have a number of primaries also growing exponentially. Or the number of quasi-primaries and d equal to 2. So, well, this sounds like a potential problem, right? So we have this huge number of primaries at the high energies, and they all appear in the OPE, or have the chance to appear in the OPE. Couldn't they somehow just like the number of Feynman diagrams in quantum field theory, the fact that it grows very, very fast, it contributes to the fact that perturbation theory in high orders becomes poorly behaved. Couldn't it somehow be that this huge number of primaries, essentially the continuum spectrum, will somehow screw up our equations? So what I would like to argue is that the answer is no. The answer is no. So what I would like to explain is that the series that you get by using OPE and by reducing to conformal block decomposition of a 4-point function, it's a very rapidly convergent series, always. So the fact that you have lots of terms associated with higher dimension primaries entering at high dimensions, that fact is always compensated by the fact that the OPE coefficients of those primaries are going to be tiny. So you have lots of states, but with tiny contribution, and the total contribution is going to be negligible. So there is some kind of decoupling theorem, if you wish, that in a conformal field theory, the contributions of states of very high dimension contribute negligibly to 4-point functions of operators of low dimension. And the nice thing is that it can be shown completely generally. So you don't need to solve the theory in order to show it. Like any theory that satisfies this. So let me explain why this is so. So the argument, so I already introduced here radial quantization, and radial quantization is, in fact, the simplest way to convince yourself in this fact. So let us translate everything, OPE, conformal block decomposition, and so on, into the radial quantization language. So the P is easy to translate. So we formulated the OPE as the fact that we can replace the product of two operators by a sum of operators and their derivatives inserted at the origin. Well, in the radial quantization, we associate an operator inserted at the origin with a state the radial quantization state, which is obtained by applying this operator to the vacuum. That's same thing in higher and in 2 dimensions. And now, if you take this state, and if you act on it with the operator phi of x, then you're going to get, again, some state in the radial quantization, but that state is not going to be an eigenstate of the dilatation generator. So it's, it will have a decomposition into eigenstates of the dilatation generator. And so what the IP means is that this state can be decomposed as the sum of the states corresponding to primaries, delta O, inserted at the origin. And then terms which you obtain here by acting with derivatives, it means that here I will have states which are obtained from the primary state by acting with the derivative operator, by p mu. So you will have here a state delta plus 1, delta plus 2, and so on. And since this function c is fixed, it means that the coefficients of all these descendant states, they are completely fixed. They are known. You can compute them, except for overall prefactor, lambda O, which is the same as in this theory. So, so you see actually, if you view things this way, then it becomes much easier even to convince yourself in the very concept of OPE. Because, you know, usually the OPE is justified that by appealing to path integral, well, let's just, you know, locality and so on. Well, isn't it obvious that if you bring 2 operators together, then clearly it's obvious, right? But if you view things this way, then you don't have to wave your hands, right? You have a Hilbert space. That Hilbert space has a basis. The basis is associated with operators, primary operators and their descendants. Now, every state in the Hilbert space should be expandable in that basis, right, to have a consistent Hamiltonian formulation of the theory. So we know that phi of x delta phi should be expandable in that series. You don't have to assume it as an extra axiom. This is just the usual quantum mechanics, right? And so you know that such an expansion should exist a priori. And once you know that it exists, then you can use conformal symmetry in order to fix all these coefficients in terms of the first one. So this provides a nice, if you wish, this is the proof of the OPE. Now, let's go to the 4-point function level. So we have a 4-point function, and what we wrote for it was the partial wave decomposition of this form. Now I want to translate it into the radial quantization. So I take this 4-point function and I go to the cylinder. So I said that so once I apply the Weil transformation, and here I just chose the origin with respect to apply the Weil transformation, I chose it arbitrarily. So once you do it, then you will get this 4-point function, these operators phi, they will get transformed into some points on the cylinder. And you know, if you do it, if you choose the origin arbitrarily, then these 4 points, they're going to be kind of in random positions on the cylinder. Like here, I inserted them here. Now, but nevertheless, okay, let us suppose that there's going to be some distance along the cylinder between the first 2 points and the other 2 points. So the distance which I denoted here, tau. So this is not a strong assumption. It just means that in the original, in the flat space, I found a sphere which separates 2 points from the other 2 points. And that sphere was mapped, when I went to the cylinder, that sphere got mapped onto this sphere. So that's all. So now I translate everything into the quantum mechanics on the cylinder. So this is my correlation function. And on the cylinder, I compute this correlation function as follows. I do quantum mechanics. So here at -infinity, there is vacuum. on this vacuum, I act with two operators, phi1, phi2, and now I can expand the result of this action into the eigenbasis on the cylinder. So this is the basis of states n. Now I take this basis of states n and I propagate every state for the time tau along the cylinder. And in quantum mechanics, in Euclidean signature, propagation just means that I gain a factor e to the minus en tau. And then I annihilate the state n into the vacuum by acting on it with phi3 and phi4. So on the cylinder, my correlation function is described in this way. And by doing things this way, I'm obscuring conformal symmetry of the problem, because I chose arbitrarily the origin around which I did the radial quantization. This is just like a normal field theory. If you quantize things Hamiltonially, you have to choose the direction of time, and this obscures Lorentz invariance. Well, here I also obscured conformal invariance, but what I gained, as we will see, all these convergence properties, which were not at all obvious in flat space, they're going to become now completely trivial in this description. So here I'm just recounting these questions. So is this series convergent? And on the one hand, it's kind of obvious that it should converge, because this series represents the 4-point function, and the 4-point function is a finite object, so this series better converge. But this is not good enough, because first of all, if you truly believe that the series converges, then you should be able to corroborate your claim by showing how fast it converges. So if you just show that it converges, but you cannot explain how fast, then it means that really you don't understand the problem. So we have to explain how fast. And the second subtlety here is that this series is not a positive definite series in general. So here there are pluses and minuses, because these OPE coefficients are not, these matrix elements are not positive definite. So it would be a logical possibility, which we would like to exclude, that this series converges because of consolations between positive and negative terms and so on. And if this is how it converges, that would be a disaster for our program, because it's very difficult to deal with such series. So what I'm going to do now, I'm going to make a break, 10 minutes. Or 5 minutes maybe, and for questions and just for relaxation, and then I'm going to explain you how it converges and then what we can do with it.
Any question now, or just this one?
You mentioned that one would need something like modular invariance as a fixed rate requirement.
Yes.
What would it be in 3 dimensions?
Well, it would be the same as in 2 dimensions, in the sense that you would like to require that the conformal field theory put on a torus on T3, and with partition function computed with respect to different slicings of this geometry should give you the same result. Except that it's very difficult to relate this requirement to the CFT data. Because in 2 dimensions, the torus is the same as the cylinder, and we know that the energies of the states are the same as the dimensions of the local operators. While in 3 dimensions, the torus is a different geometry, so yes, this requirement is there, but how to compute the relevant objects in terms of the CFT data is an unknown problem, is an unsolved problem.